All right, so what does it do? D sends out a REP. See? A special RREP is sent upstream to tell the upstream nodes that something has gone wrong with F. Okay? From the RREP, node A sees a broken link towards F, and so initiates a search. Okay, initiates. New route is searched as in the initial search, RREQ. It goes to RREQ. Okay? So he does an RREQ, again the same thing. What will happen eventually? We'll find that E is a neighbor of F, and then they will be able, and F will respond with the RREP, root reply. And so now you can re-establish the thing. Okay? So that's how you do it. Okay, and of course the old records will be deleted from the table, because there's no use already. So that is AODV. Any questions? All right, then let's go to DSR. Now DSR has a similar mechanism. All right, it also has the root discovery approach, slightly different though, and also root maintenance. All right, so again, it broadcasts, the source will broadcast a packet containing the address of the source and the destination. If the packet has been received before by a node, it will discard it. Each node checks whether it knows a route to the destination. If it does not, it adds its own address to the packet and then forwards it on. So what happens now is that the root request packet that is initiated here, every time an intermediate node passes it on, it adds its address inside. So eventually, the root request packet will arrive at the destination, and you can see the whole string of predecessor nodes, right? That way, you can go back to the source. So that's where it's different. So in DSR, you don't have root tables. It uses this sequence of predecessor nodes to get back to the sender. So this establishes the path between A to F. Got it? Okay, so different mechanism. So again, we have a sort of illustration here. So you've got all these nodes, and one wants to send data to N8, but needs to find a path. Okay? All right, the source broadcasts a packet containing the address of the source and destination. So he sends it out. Okay? Sends it out. These guys don't know how to get there, so they send it out. Send it out. See, you're adding all the addresses, huh? So this guy will discard this because he has seen this thing before. Then again, cannot find. Continue. See, he keeps adding. Right? The other side also add. Now, they found that these are all the linkages that are possible. Right? And based on that, it has a root record there to find its way back. Okay? Alright? And based on certain cost factors, they may find that certain paths are better than other paths. Alright? So, sends a reply, back, back, back. So now you have established it. Okay? So, in DSR, you keep adding the address of the intermediate nodes into the packet that is trying to discover the root request packet. Okay? They don't call it a root request packet, but that's basically what it's doing. All right, to allow the destination to find its way back. Okay. Again, there is root maintenance when it breaks. Okay, so when it breaks, then what happens is that the node that detects the break will send a root error message. Okay, RERR. Okay, so let's say example here, D to G broke. Okay, so it sends a root error message. So now the cache has to be updated. because the thing that goes D to G is no longer valid. So then A will initiate a root maintenance, same way. Okay? Any questions? Okay, the last one will be this DSTV. So DSTV is not an on-demand protocol. Not, okay? It is a table-driven protocol. That means it has to build up and maintain a table of the network. Okay, DSTV. All right, so that's the paper, the details. So the root is based on finding all the different paths using Bellman Ford. So we've done Bellman Ford already just now. Okay, Bellman Ford. So each node maintains a routing table in terms of the number of hops to each destination. Remember how much information that overhead here that you have to maintain. So it cannot be for a very large network. Huh? Cannot be. So the routing table updates are periodically transmitted. Each entry in the table is marked by a sequence number. Again, the sequence number is to indicate the age of the information. Which helps to distinguish stale routes from new routes. All right, and also to avoid loops. And new route broadcast contains destination address, number of hops, sequence numbers. To minimize the routing updates, either a full dump carrying all available routing information is done, or a selective dump, a smaller incremental part of it. Full dump is very, very costly to make it. Okay, so you can use one or two. Now, I'm not going to go into details about it because, as I mentioned already, it uses Bellman Ford to maintain this information. And you saw how we build the whole thing, right? Bellman Ford is now. Okay. The last one that I will cover is ZRP. ZRP is a combination of on-demand and reactive. Okay, it's a combination of two. It tries to bring together the best of those two. All right, how does it do it? As follows. It has both the proactive and the reactive. So what it does is that it partitions the network into zones. Okay? And each zone has all these border nodes. These border nodes. Border nodes, that means that these guys are also belonging to a zone that is a neighboring zone. And they are the relays between zones. Okay, relays between zones. All right? So within the zone, which is smaller, it uses a proactive protocol. That means it keeps the table. All right? Between zones, it uses a reactive protocol. So in other words, if something is not in my zone, then I will ask my border nodes to find out from their zones that they are attached to. And that's done reactively. Okay? All right? So the intra-zone routing is done by these border nodes. All right? This is an example here, these border nodes. The inter-zone routing is done by the table because you maintain the table, because there are less members there, so it's easy to maintain. Okay? Right? That is the inter-zone. All right. So here's an example. Each circle is a zone. Think of it, each circle is a zone. And so we see that we have some border nodes. So this guy is a border node between these three zones. H is another border zone, B is another border zone, G is a border zone, okay, etc. All right, so let's say I want to find S first. You want to find from S to D. S is my source, D is my destination. So what does it do? S will ask, hey, in my zone here, anyone seen D? No, nobody's seen D. All right, because it's not my zone. That is using the table, you know, because you're maintaining a table there. Okay, so as a result, cannot find D, he will ask the border nodes. What are the border nodes? C, H, and G. S will broadcast a route request to all its peripheral nodes, peripheral or border nodes. It's not called border nodes, peripheral nodes. C, H, and G will say, hey, do I know D? Okay, do I know D? No, I don't know D. I don't know D, I haven't seen D. Alright, so what happened? C, H, and G will again announce it to their peripheral nodes. Okay? There. B, this guy will be F and E, and this guy is A. Ah, got here. Hey, D, I know D, I know where's D. Alright, so now you have to reply back to S. So that is what ZRP is. Okay? You found it already. Alright? And then you have to reply back to S. Okay, got the idea? Huh? So by partitioning the network in this way, you try to make the best use of table-driven and reactive. Table-driven to manage a more a smaller cluster of them using a table, and then for further apart, you use the peripheral nodes to figure out what's happening. All right? Okay? So that becomes your root now. S, H, B, and D. Okay? All right. So here's a little summary of these four guys, and one more, because also WRP there. All right. In terms of various characteristics, in terms of the root acquisition, the discovery, the delay, the multi-path capability, and so on. All right. Okay, this is a summary. Here's a little bit more for different type of conditions. The next one. All right, in terms of root acquisition, discovery, etc. Okay, have a look at it. There's no perfect protocol. Some are better than others. All right. So finally, these are the other considerations. I already mentioned about scalability. Okay, earlier. How large can an ad hoc network grow? Okay, no one really knows. Okay, but it can be quite big if need be. It can be quite big. The bigger it is, of course, latency will be affected. It takes longer to discover your root, the bigger it is. For QoS, does it operate for different type of QoS? Again, this has relevance to the scalability, okay, because it's a multi-hop network. So if you have a multi-hop network, if you have very time-sensitive data, it may not work. It may not work well. Okay. And does it interoperate with the internet? Sure. Today, that's where the domain of what we call heterogeneous network comes in. HETNet. Okay. All right. So in that case, you will have an internet gateway between the ad hoc network and the internet. Not a problem anymore. Okay. And then that ad hoc network will be advertised to the internet via this gateway. All right. And with that, we complete this chapter. Questions? All right, if there are no questions, when we meet next week, I will go to the rest of tutorial 2, the last 2 questions, and whatever questions that is doable in tutorial 3. All right, and then after that, we will look at wireless mesh networks. Okay, wireless mesh networks is a variant of ad hoc network. It's a variant because it always has some sort of a gateway to a backbone network. As a variant. Yeah.
Does it apply that we are making a phone to someone?
Well, We don't normally use ad hoc network for that.
No, I mean the routing.
The what?
The routing.
The routing. For telephone network is different. It's hierarchical. It's hierarchical, telephone network. Okay? So, in Singapore, we have all these telephone exchanges. The one that service area, as I mentioned, is in Dover Road. Okay? Then, from Dover Road, they are interconnected, okay, to one international gateway. Alright, I don't know where that is. I'm suspecting it's probably at Com Center in Somerset. But it may not be there. I'm suspecting. And then from there it goes international. Alright? We are such a small country that we don't have area codes. Most other countries have area codes. Right? Okay, because we're so small. The only area codes or pseudo area codes that we use is 8 and 9 for mobile. Pseudo. Right? So sometimes you think in a form, country code, area code, what is area code? We don't have area code. It's so big a country, no area code. Yeah. Next week? Yeah. A holiday is only Tuesday and Wednesday. Okay, so there is class next week, the usual. Okay? Any other things? Okay, thank you.